It's gotta be around here somewhere. I just know it. Good thing I brought my trusty controller. I just hope that the Bluetooth doesn't fail. Oh my god! I found it! The Grimace Shake! Oh no! I've lost my Bluetooth connection, and there are two devices available. I must choose the correct device, or I'll surely die. I made it. Finally, I can taste the Grimace Shake. Happy birthday, Grimace. I am back, and today I have finally brought you guys the Unity Games trainer tutorial. In this video, I will show you step by step how we can create an incredibly simple trainer that will change the game's instructions for our game. This can be infinite ammo, infinite money, or infinite anything. It's your trainer. This trainer will work after restarting the game and also on different computers. That means you can share your brilliant trainer with your friends. But before we begin the tutorial, always read the terms of agreement for your game so you don't break them. The tutorial will be divided into two parts. Part 1 is finding the byte instructions, and the second part will be coding the trainer. The tutorial is made to be followed from start to finish without problems, but if you want to copy and paste it, then you can find it in the Buy Me a Coffee page. Here you also get other stuff and a direct link to chat with me in the Discord for only $5. Alright, so we have our game ready. I have chosen Helltaker, which is a turn-based puzzle game of some sort. And you have a certain amount of turns. I have 22 now, and when you move the character, he loses a turn for each step he makes. So I have 13 now, and if I lose them all, my character obliterates and I have to restart. So I need to solve the puzzle before my turns run out. So for our trainer, we will try to remove the function that decreases our turns. And to do that, we will need Sheet Onion, and yeah, that's it, Sheet Onion. But before we start, since it's a Unity game, it means the game is made within C#, and because it's made with C#, so on, it's for the compilation happens in real time, which is different to your usual C++ games and the games that I've shown earlier. So the Dead Island trainers and so on, it will be different. It will not be static anymore. And because it's not static, it's dynamic, it changes. We will need to figure out a way behind that. And as our first step, let's find those terms. So I'll open Sheet Onion. We have Sheet Onion here. And let's attach it to Helltaker. Let's search for 22, since it's our amount of terms. Oh, my bad. Let's do a new scan. Go from the start. So 22, turn 1, 21 now. Search for 20, and we have one address. That's perfect. So if you have more addresses, find out which one is working, you can freeze your address. Double click here, it will turn up in this table, and just click the checkbox to freeze it, and it shouldn't go down. So you can see it stays at 19. It's frozen from 20. And when we make a turn, it goes down to 19, but it stops there. So perfect. We have our address, but as you can see in Shiranyan, it's white here in the address field, which means it's dynamic. When we restart the game, or if we use it on a different computer, so on, this will change. So our return value will be within a different address. So how do we tackle this? Now, in my other videos, we would probably pointer scan for this address, but it's Unity. Remember, it's dynamic, and we will need a new method. And for this tutorial, we will use the AOB scanning method. So go into settings, go down under, not scan settings, go under debugger options and check the use VEH debugger. Otherwise the game will probably crash most of the times. So when you have VEH debugger enabled, we will right click and find out what writes to this address. We want to find the underlying instructions which access these turns. So remember to uncheck this as well. But we made 2 turns, and it showed up here to count, and we have an instruction. We have a move EAX into RSI plus 154. 154 is the offset, RSI is some object, and it's a pointer because of the brackets. So what does this mean? It means if, or whatever EAX is, it's the new value when we have removed a turn, will replace the value in our address. And when we change this to do nothing, you can see a replace with code that does nothing. We will disable this instruction. So it's not frozen like before, but we still got the same function or the same functionality. We froze the value. So let's change it back by clicking restore with original code, and let's take a further or a deeper look into this instruction. It lies under the address 223 and so on, but like before, it's white, it's not green. So this address will change for each restart of the game. And this means we can't use this address to get these instructions either. But these instructions, these bytes, they normally don't change that much because it's logic. You wouldn't change the logic behind the game, would you? That would be weird. So if we can find these bytes, we could change the bytes and get the same effect, which was freezing the steps or not losing steps. So let's copy to clipboard. Bytes only, no address. We don't need the rest since it's dynamic, it changes. And what we can do now that we have these bytes is we can perform a new scan and use the array of byte. So copy paste our bytes and use first scan. So as you can see here, we found one address and we're back at our instructions that removed the terms. So if we would implement this array of byte scanning in our trainer, we could sort of statically find our instructions most of the times. So that's what we will do in the coding bit, but I can show you guys if we restart the game. We should be able to find the address of the instructions again. So let's skip all of this stuff. And when you're in game, make sure to change the value so the instructions get allocated, because it's allocated just in time, it's compiled just in time. But let's attach it to health taker again. It doesn't matter if we keep the addresses, but let's search for our bytes this time. We have a fresh save. We can see that our address that we used before doesn't work. Our address for the bytes doesn't work anymore. But if we search with our bytes, we get two addresses here. So if we browse this memory region, it says it's not even the correct one, but let's copy that, go into the memory view and Control G, and now paste it in. I don't know why it's the wrong address, but here we can see something. It's the same move opcode like before. If we replace with code that does nothing and move in game, would you look at that? Now we found the address again, but now without searching for the terms, and we have our method of getting or creating our trainer. So let's code the array of byte scan and this memory patching bit. First off, we will create a Forms application with the .NET framework. Second thing will be to add a checkbox to enable our trainer and then access our code by double-clicking the form. Here we will create a new class that will do the array of byte scanning, or AOB scanning. To scan through the game's memory, we will need some imports. These are open process, read process memory, and virtual query X. Plus the memory basic information structure. If you think that it's a lot of code already, then remember that you will not need to do this every time you create a trainer afterwards. This is just the groundwork, which you can copy the class in the next trainer. Now we will create the main method. It will return a list of int pointers that share the byte sequence that we are seeking. The parameters will be two strings. The first one is the name of the process, and the second one is the byte sequence. We get the process from getProcessesByName method, and then open it with our imported openProcess function. After that, we create some variables to hold our information, which will be used within the loop. The last variable will hold the bytes that are converted from the string. To access our precious game data, we will first use virtual query X to query information about the process memory regions. If the memory regions are not committed and not protected, we will continue and create a buffer to hold the memory region and then attempt to read it with read process memory. If we could read the memory, then we start to compare the memory to our signature. We create a boolean that is set to true until proven otherwise. We compare each byte within our signature with the buffer, and if any byte doesn't match, we set it to false and break. If we do get a match, then we will add it to the list of addresses. The last step before the end of the loop will be to move to the next memory region. We do that by adding the region size to the address variable. This will continue throughout the process, and when we are done, we will return the list of signature addresses. Now we're done with the scanner. Let's test it by scanning for our byte sequence. Go back to the form1.cs, and here we create a list of instruction addresses. After that, we can just use our scanner class with the correct process name and the byte signature. It's important to have it in this format. I'll also add a variable to breakpoint the application. I suggest you do the same. That's not good. That's a bit many addresses. Alright, so I found my typo, and here it should be does not equals, it should not be equals 0. That's my bad. It made the whole trainer not work, but when we have fixed that, we can check inside the game again. So let's search for this string. We have a breakpoint in the test variable, which means nothing, but when we look here at the watch, we can see that we have 7 results. So it's a bit more than the sheet engine results when you search for an array of bytes, but you can see that we have one address that looks promising. So there's one C address. Let's open sheet engine and take a closer look if it's the correct address. So I'll take her again. And let's take this address. Add, or we can go into the memory view. We control G, paste, and here we can see what we had earlier. So it's the same bytes, and as you can see, it's the same move EAX into RSI plus 154. If we replace this code that does nothing and move in game, he stays. So we have found our address of the opcodes that is dynamic with our scanner code. That's perfect. Let's complete the trainer by adding some functionality to this checkbox. So when we check it, it should write code that does nothing, which can be, you just replace this code with 90 for each byte. So 90, 90, 90, 90, and it will skip that, or it will do nothing. Nope. So under checkbox 1, we will, or you will get the function or the method of select changed, I think. If you double click on this. Yeah, no, checked change. So the method triggers when you click the checkbox, either making it checked or unchecked. And here we can check if the checkbox is checked. If it is checked, we will loop through our list and just nop it. So, oh, we don't have the swedz library, my bad. Let's add the swedz library real fast. My game is 64 bits, so I'll get the swedz 64. There we go. If you haven't already, go into properties under build, general, and choose the correct platform target. 64 for 64-bit, 86 for 32-bit. But enough of that. Let's initialize the swedz library as well. So let's just go here and write using swedz 64. Here we write swedz, and in the load method we will initialize it. So swedz equals new swedz, and we write the process name again. So these libraries are working parallel to each other. They are not the same library, which means we can't use swedz.find addresses. I don't think I'll add this to the swedz library either, so we'll just have to live with writing the process name 2 times. But when we have the swedz library all loaded, locked and loaded, let's use the nop again. So we have an address and we have some bytes. So it's an int length, and to get that we just count the number of bytes. 1, 2, 3, 4, 5, 6, which means we will nop 6 times or do nothing 6 bytes. So that's the first checkbox, or the checked boolean. So checked and now unchecked. So everything that is not checked will write back the original bytes to restore it. Otherwise you will just have God mode forever. Or first my bad. There we go. So let's write the bytes. And now we can just copy paste the bytes from earlier. And there we go. So we can remove this. And let's check if our trainer works. Yeah, the original bytes are there. Here we have our beautiful trainer. And when we hit it, nothing should happen. It shouldn't crash if you have done it correctly. And we can go in game, move the character. No turns lost. Perfect. Amazing. still works at the second level. This game is actually pretty fun. It allows you to train your brain a bit. But that's pretty much it. You can add more checkboxes and write more code to do more cool stuff within your Unity game. You can search for other structures to find objects, to find perhaps the Unity scripts, I don't know. You can find whatever you want with this code. So, thank you guys for watching, and I'll see you in the next episode. Actually, I forgot to test that it works even when we restart the game, so let's do that real quick. And an interesting phenomena or thing is that the bytes haven't been located or allocated yet. So if we search for our byte string, it won't actually appear. So just to show you guys, I'll start the trainer now. Here it's watching for stuff, and if we do that, nothing happens. So as you can see, it's 21. It's not working yet, but when we first moved the character, it actually allocated instructions for the character to move. It's a bit tricky, but since we have moved the character, we should now be able to find the stuff. So here you can see it processed something, and let's hope now that the infinite turns now works. And it does. If you look at that. So don't be scared if it might seem like it doesn't work at first, but thank you guys for watching.